educational event. So please, Gert, please feel free to share your screen and start the presentation.
Thanks so much, Eliza, Malika, and Charlotte. So let me share my presentation here. Okay, so it's my great honor to give the first tutorial in this series. And so I'll try to make this a bit broader than the specific topic that I'm highlighting here. And since this is a series on neuromorphic computing in general, I'll give also a brief intro to the field and how that is now motivated by efficiency in general of computing. So please feel free to interrupt me anytime for questions. I can't see anyone here. This is, we're still in a Zoom mode here, right? But so if, I'll see if you can observe the chat, or but so if there are any questions, just feel free to just raise your voice and just ask the questions directly.
On my side, I can leave the video on and I will monitor the chat while you talk then.
Great, thank you. Okay, so this is about, well, neuromorphic computing, and with a green color to it. So we're all aware of the need for a greener society as we're facing these challenges of global warming or this climate change. And so neuromorphic engineering can also do make its contribution to make our planet a better place to live. And so efficiency is extremely important there. But let me motivate this by where we are now, and so why some of this becomes actually important. And you all have experienced that wonderful moment or challenging moment, depending on your perspective, right? Where society has been almost overtaken by machines, right? So we had the world champion in the game of Go, Retinas et al., who was beaten by Google DeepMind's AlphaGo. And so suddenly the world realized, hey, there is something about deep learning, or in fact, that term just became a commodity at that time. And so suddenly this has been a start of what you can call a revolution in AI that has now become really to the forefront. But it's important to consider actually that those advances that are under the hood, if you want, of this AI, artificial intelligence, are actually quite neuromorphic, if I may say. If you look what is under the hood of Google's DeepMind, beating this human here, is actually a model that is based on deep layered architectures in the brain, basically cortical representations that are layered, right, for deep learning. And then with reinforcement learning, it also encompasses models of, say, the basal ganglia and so dopamine reward conditioning that we have. So to some extent, in fact, the founders of DeepMind are actually neuroscientists who have actually quite well aware of brain science and have incorporated that in their vision of what AI should be. But so an important consideration here is if you look at, sure, yes, so the world champion was defeated by the machine, but at what cost, right? So if we generously will rate the power consumption of the human entire body to be about 100 watts, it dwarfs compared to the 100 kilowatts of power of this entire machinery, right? This TPU, tensor processing units, right, that are behind all this, the DeepMind. In fact, you can say, so yeah, sure, Google had deep pockets with a DeepMind for really making this happen. So, so this is a problem that is becoming quite acute, because now all the advances that are now being made towards greater efficiency, greater performance in deep learning come at a huge cost. Sure, yes, you have this trend towards, say, improving the accuracy almost at a constant, almost another Moore's law here, right? And almost exponential improvements that you can get in accuracy. But if you consider what is involved for making that happen, right? So sure, we're going towards better, lower error rates as we get bigger because deep learning machines, but those come at gigantic costs of all the computations that are involved, right? And this orders of magnitude for just a few percent of improvement. And those translate to orders of magnitude increases in the world's consumption or an appetite for all this AI, this new AI that you can think of. And so there are two aspects of this. Clearly, we have to come up with better algorithms and better, and neuromorphic engineering has a contribution there too. Come up with better architectures that model what the brain is doing as far as the smartness, the learning aspects, right? And how to learn efficiently. But the other aspect is also the trade that you have between number of operations and how much energy that you consume in the process, right? So energy per operation is also something quite important. And so here's a second contribution that neuromorphic engineering can make, at least with the tools I'd like to present today, right? Where you can get extreme efficiency. So sure, you may need 10 to the 18 operations, and the brain is having 10 to the 16 operations every second anyway, right? But this can be at much better costs than, say, just this gigantic energy consumption. I mean, just massive. So even down, so for 10 to the 18 would be the entire consumption of New York City for 1 month. Right? So there's a very nice article in Article Spectrum that highlights this. Okay, so clearly we can do much better than that. And so let's even compare this contrast, right? What we have on both ends. And so here is a standard CPU central processing unit, right, with some memory organization. So DDR, so double data rate type of DRAM memory that interfaces with that central processing unit. And so if you count for the power consumption, not only of the operations, basically the operations done on this chip, but also the cost of actually going off chip and get memory, right? So it's about 70 picojoules per bit of access. So effectively, you have about half a nanojoule of energy per map, right? Much less than the energy taken for doing this multiply and accumulate. But so getting that weight in in memory is very costly, and that's why this becomes very pricey. On the other hand, so on the other extreme, right, we have theoretical limits. What is the least amount of energy that is needed in order to compute, say, or flip basically a bit in a memory, right? And so those are arguments of thermodynamics, right? And basically, and clearly with thermodynamics, you have the Boltzmann distribution, and then there we have K is the Boltzmann constants and T as the temperature. So K times T then becomes energy. And sure, that barrier, right, so needs to be at least KT, right, for you to, in order to ensure that you're not dwarfed by noise, right? If you want your SNR, your symptom-noise ratio, to be at least 1, which is the very least you need to do computation, you're basically consuming KT, Boltzmann constant times temperature, per bit. And so that's about, if you work it out, is about so 10 to the minus 20, right? 10 joules that you have per operation. And there's orders of magnitude difference here. So we're talking here about 11 orders of magnitude. So clearly, and that what explains why we're consuming basically all of New York's energy, right? And if doing some computation that our brains can do much more efficiently. So what's the brain doing? Let's compare that. So the brain is doing a lot better than the CPU and the memory, DRAM memory, but still far away from fundamental limits. So let's be being bullish here. Sure, let's first see as neuromorphic engineers how we can get close and approach the efficiency of the human brain, but then let's see if we can do even a little better. And is it possible? I'll actually make an argument that we can actually do better. But it's still far away. So now all the advances that have been made for making things more efficient by field programmable gate arrays or graphical processing units with some very high bandwidth memory, basically bringing the memory closer to the compute because all the energy cost is getting memory. So sure, now, so with HBM, high bandwidth memory, you're down to 7 picojoules per bit. So you get already greater, you get great bandwidth, that's one thing, but you also get slightly better energy efficiencies, right? But still far away. Now, so the more extreme of doing the same is compute in memory, where each processor is actually a memory element as well. So we have a tight coupling between memory elements and processing nodes, right? So every bit of memory in your architecture would also be a processing node, right? And then you can get much greater efficiencies because the compute has a memory available right away, and so then you're limited mostly by just local capacitance, right? What limits the efficiency of the system. And then, so we have demonstrated before, you can get picojoules per Mac, and others have done the same. So that's now a typical number. Picojoule per Mac is quite possible. And so I'll just jump ahead here. So basically steal the bottom line of what I'm going to get at here, that in principle, we can actually do, so we can step from this computer memory all the way to techniques where we can actually recycle and recover even more than the CV squared, because the capacitance times voltage squared energy that you could typically consume in those computer memory architectures, and actually even get at efficiency, but basically recycle energy, right? Efficiencies are even better than the brain, or normally speaking. In fact, I should mention, where does this 1 femtojoule per centimeter operation come from? It's just a very simple observation, right? So we have 10 to the 15 synapses, and neurons are active about, on average, 1 to 10 hertz, let's say 10 hertz. So each synapse is activated 10 times per second. So 10 to the 15 synapses will give you 10 to the 16 synaptic operations per second that are happening in the brain. And that's the bulk of the computation, right? It's all about synapses. I mean, neurons are, you only have 10 to the 12 neurons, they're active too, right? But so there are many more synapses than there are neurons, and so they don't dominate the energy consumption, right? And so, yeah, so it's 10 to the 16 operations per second, synaptic operations per second. And so roughly speaking, you have about 10 watts of metabolic power. In fact, the brain doesn't consume even enough power to keep its skull warm enough, and that's why we have, I guess, or most of us have a haired skull to keep our brain warm enough. Right? So our brain is really efficient, and so 10 watts of power versus 10 to the 16 synaptic operations per second translates into a femtojoule, 10 to the minus 15 joules of energy per synaptic operation. Right. So that's basically. So here's the, and so. So for the remainder of this tutorial, I would like to give a few insights of how we can get there. So let me start with today's, I guess, what computers are doing, or the old school of computers, and how neuromorphic engineering will depart from that old school by what is now called non-von Neumann computation, or non-von Neumann operations, but actually I'll also show that there's even a misnomer too. So neuromorphic engineering is then about taking inspiration from biology, neurobiology in particular, in building artificial neural systems in silicon and other integrated technologies that basically inherit not only the functional organization, but also the structural organization, the way how the architecture is built in the brain, as well as the physical foundations, right? The foundations of the biophysics right, which now translates into physics of computation. And so Carver Mead, when he started the field of neuromorphic engineering, he really had a vision of having the physics of computation really guide the design, inspired then by what is happening in biology. And so learning and adaptation are really key to making this all efficient. And so that's basically the field of neuromorphic computing, neuromorphic engineering, right? So and so by taking that structural organization and that and the biophysical foundations, right? Those systems, artificial systems, not only inherit the functional performance of what the brain is doing, or at least get close to it, or try to get close to it, but also inherit its efficiency and resilience, right? Because there's one thing clearly that our brains are not only great computing machinery, but they're also wonderful at efficiency and at resilience. Right? You can basically remove a few neurons here and there, and your brain will still mostly do what it's supposed to do. Just try to remove a few transistors in a computer, and so that it won't go well. So the concept of non-von Neumann computing is actually very unfortunate, because I would say one of the fathers of neuromorphic engineering is actually John von Neumann himself. He's known for defining what a computer is supposed to do, and so defining from a very mathematical point of view in terms of the computations and the role of, say, the processing and memory, and how this all organized in a very organized fashion, right? Basically, and we're still using that framework mostly for digital computing today. But also in his last opus, just before he died, he actually highlighted the differences between computers, as he envisioned it, and the brain. And he actually made a case for having more parallel computation rather than this discrete and sequential operations now taking place in the brain. And he was actually, I would say, he was really looking at the brain and coming up with some of the foundational principles of neuromorphic engineering. I very much recommend that you read this marvel of a book. He didn't write it himself. He unfortunately died because before he could give his lectures, but then this book was compiled after his death. Yeah, it would have been wonderful lectures he would have given. So let's just contrast then this computer, and here is maybe an old version of a computer, but actually is still one of the hottest CPU, central processing unit, chips today. This was Intel's Itanium 2, and I still remember it. It was really a great thing, wonderful in terms of what it did, great specs it was doing. It gave us gigahertz rates of computations, right? And we were very excited about using it. But look what is there involved, all this level of cache, right? Cache, those are basically intermediaries between slow, vast memory and then this fast centralized computing here, right? And it's totally inefficient. So much of the energy is wasted basically moving things around. And that's basically the paradigm of what is called von Neumann computing. Again, it's not doing him great honor, but so yeah, that's the sequential model of computation, right? Sure, you can do great things with it, but what about intelligence? That's the other thing. So yeah, you can definitely play more games with it, but that's all you can do with this. So in contrast, contrasting that those computer chips against the human brain, you get this massive parallelism, as John von Neumann already has highlighted. And so it's interesting to see that actually some numbers are quite comparable. So the memory bandwidths have gotten even 10 years ago, right, or 20 years ago, the memory bandwidths are already comparable. But what is really vastly different is the parallelism of operations. Right? So even now, with the later generations of compute elements, like the superscalar processors and the CPUs typically have more cores, right? Even GPUs, right? They have multiple cores, but not more than a few hundred, right? So you have maybe at most you can think of like 1,000 or so cores in your GPUs, your graphical processing units. The brain has, you can think of having 10 to the 15 cores. Well, 10 to the 15 elements, right? 10 to 15 synapses, all basically that are 1-bit CPUs, if you want. They're, well, no central, basically 1-bit processing elements doing their computation all in parallel. And sure, at a very slow clock, just about 1 hertz, but 1 hertz, right, times 10 to the 15 synapses gives you 10 to the 15 operations per second, which dwarfs this, right? So what the Itanium or even the latest chips are doing. In fact, the latest chips are not that much faster as far as the clock. They're still operating at the gigahertz, a few gigahertz, right? So it hasn't changed. You can really go to 10 to 15 hertz. So maybe with supercomputing, with superconducting supercomputing, you can get there, but it's at a very high energy cost. Right? So clearly, parallelism is the way of making things more efficient, and actually, you can get some great efficiency also by taking advantage of the dependence of energy they consume on voltage. And in fact, it's one thing that is understood in those computers. What consumes energy is capacitance times the voltage squared, right? And why is that? Because, well, so you have charge that you need to, right? You need to move charge, right, in order to just charge your node in your circuit, right? And that charge is capacitance times voltage. C times V to D is how much charge you need to move on every node. And so in every cycle, that charge is delivered from V to D, from your power supply. And at the end of the cycle, it gets returned to ground, right? You're basically, right, the drain, right? So in the process, you have moved C V to D of charge from V to D to 0. So the entire energy that you have consumed in the process, right, in one cycle of going up and down, right, with the clock. So every clock you have basically consumed the product of the two, voltage times charge, right, which is V to D times C times V to D, right? So that gives you C times V to D squared. So again, C is capacitance, V to D squared is the supply voltage squared, right? So that's the energy that you consume for every operation. And so if you do that at the clock rate, so the clock rate times that C V to D squared is the energy that you consume, right? So with massive parallelism, right, you can go much slower, which means you can bring your supply voltage down. And so bring your supply voltage down allows you to lower the energy per compute, right? So with massive parallelism, you're still in the same compute, right? But each computation now involves much less energy because you can bring the supply voltage down. And so there has been one realization, and that has helped at least digital computing to get better efficiencies, but still far away from what the brain is doing. So I'll give an answer to other observations you can make here. But so let me actually frame this in a few other giants. In addition to John von Neumann, we had Richard Feynman, Nobelist, who was telling us many things. So he started really the field of nanotechnology, if you want, right, by telling us there's lots of room at the bottom. And so he made us really think about, in fact, driving the technology, the information technology revolution by basically nanoscale of integration of silicon. And Carver Mead actually coined the term Moore's law. He was a good friend of Gordon Moore at Intel. And so Gordon Moore saw this evolution happening, actually revolution happening in the scaling of microelectronics technology, right? With this doubling or this of density, right? And basically the density, right? Every few years, right? And so that was known as Moore's law, this exponential trend of increases in density, shrinking feature sizes of technology that made everything better, right? Because efficiency went up because capacitors are smaller, right? The voltage can go down, so it gets CVD squared goes down, so everything gets better, right? And so Moore's law has been a fantastic thing. Carver actually really had analyzed the scaling of this technology very beautifully in his first book on digital VLSI systems. But so the two are also well known, actually less known for really starting the field of neuromorphic computing. So Richard Feynman actually, the last thing he wrote just the day before he died, this was on his blackboard, right? What I cannot create, I do not understand. Right, so if you really want to understand something, you have to build it, and so that's the argument for analysis by synthesis, which Carver Mead has taken to the extreme by starting this field of analog VLSI and neural systems, neuromorphic engineering, basically build brains from the ground up, right? And so this has been a fantastic journey now the last 30 years. It started at Caltech with Carver Mead, and they had a whole group of people that. And many of them are now, I guess, everywhere, but some, including at ETH Zurich at the Institute for Neuroinformatics, right? You have now several of the founders of the field who were there with Carver, right? They're actually there doing great work. And so a few other places. I was just also lucky to be around at the time. So, so there's a community of people that really benefited and that started this field of neuromorphic engineering in stealth mode. And it is all about analysis and synthesis. So analysis is about figuring out or understanding how the brain works in a top-down method of analysis. Is basically what neuroscientists are great at, basically reducing complexity by basically isolating concepts to be studied, right? And so that's really analysis is really science, right? Now synthesis is the conjugate, and that's what engineers are good at, right? So engineering is all about synthesis, putting things together as a systems approach, building things from the ground up, right? And so the two can go now together because it just so happens that for the different levels of scale that we have, right? So at each level of scale in representation, there are isomorphisms between what is happening in silicon versus what is happening in biology. And so this happens, so Boltzmann distributions appear everywhere here, in fact. So you have Boltzmann distributions that happen here at the network level. We can model Boltzmann machines as an Ising kind of model of what the brain is doing at network level, and build circuits that embody the noise. It's a model of Boltzmann machines that we can really implement in silicon too. But actually, even down to the very lowest level of ion channels, ions moving to ion channels versus electrons or holes moving through MOS, metal oxide semiconductor, field effect transistor channels. In fact, you have channels in transistors, you have channels in biology that basically have transport going through membrane of your of your cell. And so it just so happens that you have this nice isomorphism there due to the following. So here is basically what a transistor looks like. And so I guess maybe I don't have to go over this in detail, but so, right, so you have this transport from source to drain, right, electrons in this case would flow, and basically mediated by what happens on the gate, because the gate is really a potential generating mechanism, right? So the raising the gate voltage will attract more electrons, get more charge that builds up, and it creates a channel for transport between source and drain. But we can really think as an energy barrier that's modulated, right? So by bringing this gate voltage lower and higher, basically you modulate the barrier for electrons higher or lower, right? So the potential for electrons is just minus is the voltage, right? But so as you raise the gate voltage, you lower the barrier and get more transport. But actually, so in the subthreshold mode of regime, in subthreshold, just below the threshold transistor, basically now you have a barrier that is positive. And so ideally, this would be basically no flow of electrons from left to right, and yet you have flow, and that's due to this Boltzmann distribution. The fact that you have a tail, a tail of this energy distribution, the Boltzmann distribution, that can still make it over the barrier. And so the higher the barrier, the fewer they can make it, and that's what this Boltzmann distribution means. You get exponential dependence, right? Of as you lower the voltage on the gate, which increases the gate voltage, which increases the barrier, right? So you get less current flowing. So you get exponential dependence of current versus voltage here. And so the opposite is true for a PMOS transistor, so a P-channel device. Basically, here you have holes. So there, if you increase the gate voltage, and actually, in this case, you increase the barrier, right? So then you get exponentially less current, right? So, and you have this dot here that denotes that complement, right, of the action for the PMOS versus NMOS. That's almost a tutorial on CMOS technology. So for those of you who are neuroscientists and haven't seen anything about transistors, that's a very brief intro. But so here's, because, and so for neuroscientists, if you look at conductance versus voltage that you have for this ion channels, so as you raise or lower the membrane potential, then you look at the conductance, basically, right? So if you have those ion channels, right? So if you look at the conductance of current flowing, these ions that move through those ion channels, right? So that conductance will have also an exponential dependence. In fact, those curves of current or conductance versus voltage are not any different from the curve that you have for this transistors in subthreshold, below the threshold, right? Basically, where you have this positive energy barrier. And in fact, there's also this above threshold regime that is quite similar. But the point here is that you have this massive dynamic range, orders of magnitude of conductance for very small changes in voltage, right? Owing to this exponential dependence that can really, dynamic range can be harnessed for doing computation. And biology has harnessed this, but until neuromorphic engineering started, that has not been harnessed in silicon. So the field, so what Carver realized is, let's make circuits that really can take advantage of the same mechanisms, right? And actually then directly innately implement what is done in biology, right? With the subthreshold transistors, and having this orders of magnitude of dynamic range with currents, which for the transistors are in orders of, so that would be from femtoamps, well, maybe or picoamps, up to hundreds of nanoamps. So that gives you several orders of magnitude of range. And also there's small currents, which also means you get low power consumption, which can be harnessed if you do it right to get low energy per computation. Right, so that's the beauty in a way. And that's in a summary, that was all the excitement about initial neuromorphic engineering, like it's now 30 years ago, more than 30 years ago. And by the way, you have the same dependence also with synapses, right? Quite exciting. So you can start building circuits that have elements that inherit those kind of properties. Silicon Retinas, so Cauwenberghs, when he was at UPenn, was doing this chip here, but he has done many more since then. The whole community has been doing Silicon Retinas that model basically what the retin ganglion cells are projecting over the optic nerve to the rest of the brain, right? And so they're all spikes. You get spikes that spikes over the optic nerve will capture quite well what is happening. You can reconstruct the visual scene just from the spikes, right? So they can be harnessed for doing with neuromorphic circuits, right? Can be harnessed to doing doing compression on the focal plane, basically doing motion sensing. And so there's a whole range of what they're called dynamic vision sensors, right? That take advantage of this temporal coding on the focal plane for extreme efficiency of coding events. In this case, temporal events as spikes, right? Registered on the focal plane. Right, so then the field of neuromorphic engineering over the last 30 years has converged on this address event representation. Basically, spikes as being the language of the brain, right, of computation in the brain. So have this efficient system that take advantage of those events, the sparse events, and communicate the sparse events over, let's call this address event representation over a common bus. Right, basically, so neurons that fire have a unique address, and you send those events over to other regions in the brain over the white matter, these fiber bundles that are now instantiated dynamically rather than making literally white matter with fiber bundles. In silicon, basically, they're instantiated by basically making lookup tables and memory architectures and basically communication infrastructure as an internet, right, for communicating spikes across even multiple chips. Right? So that's a scalable, reconfigurable means for constructing large networks that have arbitrary connectivity and even plasticity. Right? And so just, I'll actually skip this, but so the point here is that with neuromorphic computing, you can actually do computation that is very different from traditional, what is called von Neumann, basically this AI systems, or traditional AI, symbolic reasoning, right? So it's all about deep search, deep efficient search. It gives you basically a complexity or a cost of computation that is at best linear in the task complexity, just by construction, right? If you want an exact answer, you need to go through the entire search space. There's no way around it. And so this analog, collective analog computation, this learned habitual cognition, right? This deep learning, rather than this deep search, right? We'll look for representations that are approximate, but on scale that are still doing quite well. In fact, that generalize even better, right? That generalize well. And so you can get the scaling properties between task complexity and machine complexity that are much more favorable, which means you can do a lot more with less. And so you can quantify this in terms of task energy efficiency. Energy per task is energy per operation times operations per task. And I'll focus here mostly on energy per operation, right? This femtojoules per kinetic operation is what we're going for. But there's also a complementary task of minimizing operations per task, right? Which can be done by better neuromorphically inspired learning algorithms. Right? And then I'll skip this for most of this tutorial here. I'll focus mostly on the blue here, the energy per operation, basically done by nanoscale integration and basically physics, nanoscale engineering that can give this massive scale, massive densities at great efficiencies, right? And that's what we're going over. And I'll skip then the neuroscience / AI / deep learning / neuromorphic algorithms for actually learning with the architectures. So here is a summary of some systems out there and their limits. And so this tutorial being about efficiency. So those are, and it's not a complete list, but so this is mostly systems that are reconfigurable with spikes, and they have large number of neurons, right? And so they're all being reconfigurable. So so any neuron in principle can connect to any other neuron, and that's all defined in this event-based representation, right? And so you have neurons ranging from a few hundred to a million here, right? And so you recognize IBM True North, Intel Luihi, also the Spinnaker system, so Manchester, and also developed at Dresden. So they're analog chips, because at Heidelberg with the facets and brain scale system, Stanford, yet Neurogrid, and so at UCD we developed the integrated fire array transceivers. And so what we can see here is that energy efficiencies range in around a few picojoules per synaptic events, and so that's worse than human brain, clearly, 1 femtojoule. But still better than doing this computation on a digital computer. And so how do you actually improve that efficiency? Well, so one important consideration is to make it really scalable. You need to ensure that the white matter is taken care of, and so your connectivity needs to be hierarchical. And so hierarchical as event routing will give you both this tree-based architectures for implementing small world networks where you only have a few hops to the network in order to reach any point in space, right? While still having the arbitrary connectivity that we have of this local connection at each leaf node in this hierarchy, right? So basically the white matter is basically this trees implementing this connectivity, and then the gray matter implements this arbitrary connectivity that we have with flexibility, right? So that's the best of both worlds. And so higher is a means for doing that. So here, so higher then stands for this hierarchical organization, where we have this a tree of nodes in the network where we just do message passing from one level to the next level. And so you only communicate source addresses rather than sending all the events, right? And so at the leaf node architecture, you have those efficient processors that do actually the computation, synapses and neurons, etc. So then you have local memory that couples to implementing the actual connectivity in the network. Right? And so now, and the efficiency of that representation here, if you do this analog compute, right, for doing this neural integration, right, this two compartment, right, so you have a soma and you have a distant part, right, and so you have synapses and dendrites are also basically they're represented here in analog, but then when it spikes, sends out an event, and an event goes through this system around it. So you go through memory tables that figure out now synaptic input going to some other neurons and perhaps neurons elsewhere in other systems through this higher framework. Right, it's all great, but so the efficiency that we accomplish here is about 22 picojoules per spike event, synaptic event. And so how can you do better? Well, so what is the limitation here? It's really the efficiency of getting, I mean, in fact, most of the energy is consumed here by going off chip, and doing that operation here, basically going through to memory. And that can be improved by bringing memory much closer to processing, right? And so, as it so happens, all this emerging memory technologies, right, whether it's called an RRAM for resistive RAM, or here this is phase change memory, PCRAM, or MRAM, or magnetic RAM, right, or STRAM, and there's different associations of conductance-based memory arrays, crossbar arrays of memory elements, right, where the memory is encoded as conductance. And so you have this word line that activates this conductance onto the bit line for basically as a digital memory. But there's no reason for you to do it that way. You can think of the word line as being a presynaptic action potential that activates your postsynaptic membrane conductance, right, onto now the dendrite that you have here, the bit line. So right there you have a biphysical synapse. And so you won't have to do anything as far as the technology. You can use the same memory technology. So all the $1 billion of investment that you have in improving this phase shift memory or RAM, like this resistive RAM technology, can be directly leveraged just by interfacing those arrays, those crossbar arrays now with neurons, neural arrays, right? And so that allows tremendous enhancements not only in neuromorphic technology, but also in the way those memories are operated, right? Because now they become much more efficient. Now you can do, rather than each memory element being sequentially accessed as in digital memory, now each element is now doing the compute right there. The multiply cumulative is happening there, right? You present inputs along rows here, and you get outputs along columns, or vice versa. And so you can get this massive vector matrix multiplication in one clock cycle. You get this entire matrix multiplied by the vector, right? Because you have all this owing to current, Kirchhoff's current law, you get all this parallelism happening. So there's a whole field now of memistive neuromorphic computing that has been embracing that concept of this crossbar arrays of those elements. And so you can start integrating those crossbar arrays of synapses along with arrays of those integrating fire neurons, right, at a coarser scale underneath. So you can have this finer scale synapses on top with the coarser scale neurons underneath, and so you can get the direct, even more direct, right, communication between the neurons and the synapses, right, in this organization. And in fact, that's what we did here in this work. So with the layer 1, right, so Raj, and Ram, etc., whole team, including, so this was in collaboration with Philip Wong's group at Stanford, and also with the collaboration at Tsinghua and that whole team here. Right, so we showed, in fact, we have an archive paper that now actually demonstrates a 48 core system, right, of the same, right, so with millions of synapses and tens of thousands of neurons. All doing just AIs. In fact, we have demonstrated all the way going from MNIST to CIFAR 10, all implemented with those crossbar arrays of synapses and neurons. And so, yeah, so literally we bring neurons and synapses close together in this reconfigurable architecture that goes in both directions. So you can choose for each neuron whether you connect, right? So whether you connect a column or a row, and this way you can transpose the connectivity in an array for implementing basically, and the transpose is really the bread and butter of much of modern AI, right? If you want to implement a conjugate for doing backpropagation, you just transpose the array directly, right, by flipping a switch here. And so also for other neural architectures, such as variational autoencoders, right, or restricted Boltzmann machines, those transpose operators are extremely important for going between inference and generation for neuromorphic computing. And we accomplished a great efficiency. So now that way we're down to a few femtojoules per synaptic operation. And that's really, so it's really limited by just the CV squared, just the CV squared of energy that we have in each element here. And that's an important consideration here, is that actually the energy efficiency, if you do it right, and so if I have time, I can just go on the whiteboard and explain this. But so if you do things right, So rather than having those typical transimpedance amplifiers that will clamp your outputs, right, at 0 volts and basically collect currents across this array, that's a very power-consuming operation that limits the efficiency of those crossbars. So here, actually, what we did is we just let it float and let voltage accumulate, and so let the equipartition theorem play out. So where the energy that's actually consumed in the process of this crossbar doing its computation is just is just given by capacitance times voltage squared of the excursion you have on this node, and that is just femtojoules because you have just a few femto farads of capacitance on each node. There are other details on how we do that, and I recommend take a look at the paper, right? So how we actually then transferred that, we still go, we sample that voltage and still bring it to a TIA, a transimpedance amplifier, but that's done at a much lower energy because the TIA is now biased at much slower speed than the actual this quick nanosecond operation for activating the array. So we so we're able to do this alternating between inference and generation for this Bayesian type of inference that we can do in this architecture by going back and forth, right, between the visible units and the hidden units, right, as in this Boltzmann machine or variation autoencoders. And so that really allows to fill in blanks or missing data, right, for generative learning. So this is a generative model as opposed to a discriminative system that allows you to basically fill in the blanks as shown here. So here, for instance, you have you present a 6, and now you can perturb the 6, right? You occlude a few pixels here and there, and it becomes less of a 6. But now you let the system recover itself, and it'll fill in. Basically, goes back between hidden and right. It basically dreams, and it dreams up and figures out this is a 6, and not only recognizes it, but also generates and cleans up this 6 here, right? And it does all that at much less energy than a computer, orders of magnitude greater efficiency, right? And so we're taking, so at Telluride we have great fun with those things, and we actually so last year we had this neuromorphic systems with NeuroDin, right, for doing neuromodulation control, and so this year we'll be taking some larger systems to Telluride for doing cognitive computing that basically with 40 FPGAs, actually will be 160 million neurons and 40 billion synapses that we can cater. They're doing this massively parallel, not quite computing memory. We're using basically high bandwidth memory here with FPGAs, but so the concept is the same, right? We can get great efficiency for large scale computation. Okay, so I think, now I want to get to the attojoule of thing, right? So the attojoules, how do you go now from those femtojoules to attojoules, and we go even beyond the efficiency of the human brain. So that's work we actually did 25 or 30 years ago, 20 years ago, with Roman Janov, who was a memory in my lab, and then also Raf Karakovic, who was at Toronto. So both, so where Roman is now a full professor, right? So we did this. We demonstrated charge coupled arrays for basically those are synapses that are now not conductively coupled, but they're synapses that are actually capacitively coupled or charge coupled. So you have charge coupled devices, right, where you basically transfer charge over from the input line that activates it to the output line, and this is capacitively, basically by charge that is coupled inside the channel or in the well here, right? So the charge, so selectively as you lower the input here on the column line, that charge gets transferred over to its neighbor here, and that charge transfer induces then capacitively a change in voltage at the output, right? So this is all, and this is a non-destructive operation because you can take the charge back, right? So when you bring the voltage back here, the charge returns and there's no loss of charge, right? So the charge is conserved, and so in principle, this is a totally charge conserving and energy conserving operation. The only energy that is consumed is basically driving this line, but then we can drive that line rather than with an inverter, a CMOS inverter, where, as I mentioned, right, if you drive a line between 0 and VDD, up and down. Every time you go up and down between 0 and VDD, you consume, right? So again, the total charge is C times VDD. That's a charge you need to, right, deliver as you charge the line. And that's delivered, so the charge is delivered from VDD and returns back to ground, right? If you use a CMOS switch that way, right? So basically you have a PMOS that pulls you up and NMOS pulls you down. So the charge in one cycle, up and down, the charge has been delivered from VDD to ground, right? So, and then the entire energy is totally wasted, which is basically that the entire potential has been wasted. So you get, so that VDD times charge, which is C times VDD, has been wasted. So basically C times VDD squared has been wasted, right? So here we did is, rather than coupling with CMOS inverters, we coupled that with adiabatic energy recovery logic circuits. So basically a bunch of switches that follow a hot clock. And a hot clock is basically a voltage that, right, basically a resonance that you have in a tank where you have an external coil that couples to all the capacitors that you have in the array here, right? And at resonance, you get this transfer between magnetic energy and electrostatic energy, right? Going back and forth, oscillating at this resonant frequency, right? And so there's the hot clock, and we just flip switches, and we only flip a switch when the voltage crosses 0. That's the key, right? That's the mantra if you want for adiabatic computing, right? So you can only open or close a switch when the voltage crosses 0 at the time of this hot clock, right? And if you do that consistently, you never waste any energy because every switch either has 0 current or 0 voltage, right? So you should never have any power. And so that's the way you can really operate at zilch. And basically, this way we demonstrated that 25 years ago, just the femtojoules, a femtojoule per multiplied cumulate. And this was in 250 nanometer technology, right? Right, so, and a femtojoule per Mach again is at the level of energy efficiency of the human brain. Because with all respect to what is happening in the brain is much more than just a multiplied cumulate, but if you were to abstract the synapse is just a multiplied cumulate, 1 bit, right? So that's basically what it is. So, if now you were to take this to a much deeper submicro technology, we can go now down to attojoules, right? And so in fully depleted SI technologies, things even get much better. So I think I will, right, so, and in fact, this is showing how we actually do this. Those are the ERL drivers, right? Those energy recovery logic drivers that just, right? So basically all the capacitors in the array are basically driven. And so depending whether the bit is 1 or 0, that is determined by the bits that come in here, but then the actual line, the capacitive line across the array is then driven, right? Here. The bit lines are driven by this hot clock, right? That is provided externally with this inductor that's coupled to. In fact, all you have to do is basically you can come in with power at VDD, and just by pulling the hot clock node every once in a while, just a trickle, right, whenever the voltage is low, you give it a little trickle, and that's all you need to really keep this one resonant, right? And so this is how you actually supply DC power and actually have it resonantly coupled to the array. And so this is like a beautiful demonstration. And so this shows that if you switch between dynamic versus adiabatic, you can recover most of the energy. So if you have a tank that has a Q, a quality factor of 100, then you recover basically 99% of the energy, right? And that's how we went from the 60 or so femtojoule per Mach down to 1 femtojoule per Mach. So that's what's great efficiency. And I think I'll stop there. So basically, right? So in fact, you can go also the other direction from micropower, mixed field SI to neuroscience, where you can actually make interfaces to the brain at great efficiency too, at great noise energy efficiency, right? But the principles are the same. And I think I will end here.
Thanks a lot, Gert. I think it has really triggered interesting discussion. We already see that in the chat. I really like the perspective as well, going to the attojoule. I know your schedule is quite tight, so I have a question here: is how much time do you have for questions, or do we direct them?
Let's go. So I see 10 questions. Let's see how far I can get
Okay.
to a few of them. Yes.
So there was an ongoing discussion. So if I can summarize that, because there was quite some message exchange as to the hidden costs. Basically, for example, the training costs. It was argued that it's actually amortized over a lot of inferences later. What do you think this contribution represents, and how we can deal with that? And also the hidden cost of silicon fabrication, which also increases as the technology scales. So about these.
Those are great. Yeah, those are great questions. Of course, learning is really the challenge here, right? Inference is easy in a way, right? But how to actually transfer the efficiency that you have during inference to also doing learning. And for learning, there are two aspects. First of all, typically you need to have many epochs to the data, typically, right? To achieve a certain level of acceptable performance during learning. And that's already basically, you have to go to the data set more and more times, right? And that's very inefficient. And second of all, in fact, in a real neuromorphic application or a real scenario, you won't have the luxury of going back and play the same data over and over again. So there's an argument for continual lifelong learning, and this will be the topic of Telluride, one of the work groups that we're doing together with Julian and Bodo. So this will be continual lifelong learning with neuromorphic computing. So we'll figure this out at Telluride this summer, right? How to do this? How to do efficient learning one pass of the data? Can you just learn in one pass of the data? And so I think the challenge is out, and I think we can do it. But yes, but then there's still the cost of actually changing the weight. So that's an entirely different thing, right? Of course, the cost of an RAM or PC RAM or whatever non-volatile technology, it costs much more to change the weight than it is to access it, right? And that's a challenge that can also be overcome as well. If you don't make big increments, you only make small increments, and then the cost is actually much less than that, right? But yes, and the other question was
that makes a really great link actually to the second question that was asked by Elias Kassef. So he went to the question that, for example, if we want to learn at the edge online in an efficient and supervised manner, definitely it's not the same use case as going for image recognition on cloud servers. So what do you think are the benchmarks and tasks where neuromorphic engineering can shine?
Great question. And I think there are a few data sets. Everyone uses MNIST, right? Still, because it's so easy, I guess. But there are now neuromorphic versions of MNIST and MNIST, right, that have become quite popular in the community, and they're great because they're actually event-driven. They're actually basically they speak the language of dynamic vision sensors. So that's a great marriage because between the sensory world and what those neuromorphic computing should be doing. And so, yeah, those are great data sets. There are other data sets that will be developed that are more tuned towards the event-driven nature of a sensory world, right? So definitely, I would advocate more neuromorphic data sets. And so, yeah, I presented those MNIST or Sci-Fi 10, but of course, yeah, those are not. Those are great for AI benchmarks, but for neuromorphic, we can actually do better than that. But I think we should actually first. So I think we should take advantage of a Trojan horse in the sense that neuromorphic engineering should outdo AI before it actually really becomes its own, does its own thing in trying to get towards higher level cognition and then really captures what the brain is doing in more detail. And I think it's possible. We can return neuromorphic engineering as a super efficient AI engine and do that, of course, in an event-driven fashion with sparsity, etc. And then later we can figure out how actually the brain actually is doing more than just, of course, Sci-Fi 10 and all those things. Right? But I think it's okay to compete with AI. I think we can.
And therefore, I think that makes a great link to the last question that is in the chat that was asked by Toby. So the three main figures of merit to have a neuromorphic engineering in the industry is cost, throughput, and power and energy efficiency. And it seems that neuromorphic engineering is mostly about the power and energy efficiency, but what about cost and throughput? Could you comment on that?
Well, I hope I have given a case that throughput can be scaled with parallelism, and there is a case, right? So yeah, it's a matter of scaling things up. So having those systems all operating in parallel. And yeah, absolutely, there are challenges ahead of us. And so we all know, like I said, for instance, how do you interface these dynamic vision sensors with your compute, right? There's some serial links in there, right? There are event-based representations that are serial, but I think we can scale things up and actually make things hierarchical and really have things pan out at a parallel level. And so throughput, so in an ideal world, which I think we can get at if we do things correctly, everything will scale. Everything will scale linearly with size, right? With number of elements, right? So power scales. So energy is basically a constant cost per operation, but also throughput scales with everything as well, right? So you can take twice more hardware, you get twice more throughput, and that's actually in the higher representation, in hierarchical as event representation, that is actually adhered to, right? Everything scales, so power and throughput all scale with the number of elements that you have in the system. This assumes that fan out is constant. As long as fan out is constant, then this is true, right? But yeah, it's a great question, Toby. There's much to be done there, absolutely. And
if we massively increase the parallelism that has a cost in terms of area, do you think that overall we can reach some sweet spot compared to?
I don't think so. I don't think so, because ultimately, one way or another, you need to store bits somewhere, right? I mean, so think of your memory as now smart memory. So rather than having your terabit memory somewhere, and there's no on flash, right? You can have a terabit on flash. Think of that flash now becoming a terahertz processor. It does operations, say, let's say 10 hertz for each of the terabits. There you have, right? Something, and yeah, so I think we get massive parallelism at really great cost and at great efficiencies, right? Right? There's no cost in the way these. It's much more efficient to do that way, right? You need memory anyway, so you just bring the processing. So rather than thinking of bringing the memory to the compute, is the opposite. You bring the compute to the memory, right? You have all those advances in memory technology. Think of now what we should think about is, rather than making better chips that do the processing, let's make better memory chips where the processing is integrated in the memories, and then this becomes smart memories, smart systems, right? I think that's where the future of, actually not only neuromorphic computing, in general, that's where the future of computing lies.
Yeah, therefore I think that makes a great end, because the chat now seems okay. So let me thank you again for this great vision as to the trends for neuromorphic computing, and as well as the great tutorial value of the talk that you have given. So it was really a pleasure to have you with us.
Thanks so much, Charlotte, Lisa.
Thank you, Gert. Thank you, Charlotte, for chairing the session. And bye, everyone.
Thank you. Yeah, thanks, everyone. Great questions.
Bye-bye.
Bye.